0 because it is uniform, and the largest ascent is in the when the unit vector and the gradient vectors are actually parallel. If they are pointing on the same direction, that means the dot product of the two is going to be maximum, because cosine of 0 degree is 1, and the greatest rate of change or for descent, or the minimum, is going to be when they are pointing in opposite direction. That means the opposite of the gradient vector, and the magnitude is actually the length of that gradient. All right. And when on the level curve, when they are closer, the level curves, that means the function is really growing very fast. That means the highest gradient you are going to have. If they are far apart, it is the weakest gradient, and we'll talk about it when we are dealing with intensity of vector field. All right. Now, normal, the tangent line to a contour curve of f at the point x sub 0, y sub 0 will be given by this. Then we can have actually equation, the normal vector to the contour map, and then we can have actually equation of the tangent line. All right. So now example, find the equation of the tangent line of x squared plus y squared is equal to 13 at the point 2, 3 by viewing the curve as a contour curve of f of x. Okay, try this one and we'll work it together. Okay, so what do you have? You have x squared plus y squared is equal to 13. This is really implicitly defined function. Then if I bring x squared plus y squared minus 13 is equal to 0, this can be z, which is f of xy. So it is a function of two variables. Then we can find the gradient, the partial derivative with respect to x at the point x sub 0, y sub 0. This is going to be actually 2x, and the partial derivative at any point actually. All right. Then specifically we are given the point here, 2, 3. So you plug it in here, the partial derivative with respect to x at the point 2, 3, which is equal to 2 times 2, which is equal to 4, and the partial derivative with respect to y at the point 2, 3, 2 times 3, which is equal to 6. We have gradient. Therefore, then the equation of the line is going to be the partial derivative, this specific point of with respect to x at x sub 0, y sub 0 into x minus x sub 0 plus the gradient at that same point the y component of the gradient as well as what point, and this is y minus y sub 0 is equal to 0. Then in this case, we have 3 into x minus 2, I'm sorry, 4, plus 6 into y minus 3 is equal to 0, 4x minus 8 plus 6y minus 18 is equal to 0. Then we'll have 4x plus 6y equals 26. So this is equation of the tangent line to the contour map and so on. All right, and we'll do the same thing with the gradient vector in finding gradient on 3-dimensional vector. Okay, gradient and directional derivative for function of 3 variables. Upon finishing this section, you should be able to actually find the gradient of a function of 3 variables. Let W be a function of 3 variables, x, y, and z, hypersurface in R4, because the reason we call it hypersurface, we cannot really determine the surface in 4 dimensions. So what we have to do is we'll have to come up with the level surface for that. Just like for a surface, we can come up with contour curves. We can come up for the hypersurface level surfaces because it is 3D. So if the unit vector has a component u1, u sub 2, u sub 3, a vector in R3, the directional derivative of the function w, which is f of x, y, z, in the direction of u will be given. Yeah, the gradient with 3 components and the unit vector with 3 components. It's obvious, it's the extension, you can really handle it. So what I'm asking you is really find this one, find the direction derivative of the function w, which is given by x, y, sine of z, in the direction of vector v, which has the component 1, 1, 1. Go ahead. I mean, you can handle it very easily. By the way, can you hear me now? The voice was low before, yeah?
I can hear you.
Okay. So find this one. What we are going to do is find the partial derivative with respect to x, y, z, and that will be the x, y, and z component of your gradient. And then this is not obviously a unit vector, normalize it, and you have unit vector. And then do the directional derivative. Obviously, let us move fast. The unit vector u is going to be is the vector v over the norm of vector v, 1, 1, which is square root of 3, 1 over square root of 3, 1 over square root of 1 of 3. And if you really want to check this one, square all this and add them up, it will give you 1. Then the partial derivative with respect to x of this function is y times sine of z. And the partial derivative with respect to y is going to be x and sine z are constant, so x sine z will be. And the partial derivative of the function with respect to z, x and y are constant, the derivative of sine is cosine, cosine of xz, xy, cosine of z. So you have the directional derivative, the dot product of the two, and those derivative, except you have 1 over 3 as a coefficient in all. All right. The same thing, I will do it this quickly because you have done it and I don't want to waste time and I want to move forward. Find the rate of change of pressure at the point Q, 1, 2 in the direction of V, which has a component 0, 1, 1, assuming that the pressure in millibar is given this way, 1000 plus 0.1 yz squared plus x x squared z minus y xy squared, where x, y, z are given in kilometers. So what you have to do is the first is find the gradient. Well, this is constant, it is gone. So the x component is here, this is going to be 0, but here you have 2xz, that is what we get. And here simply y squared. And when you find the partial derivative with respect to y, this is going to be z squared, and this is gone, and you will have minus 2xy. That is what we have. And then when you take the partial derivative with respect to z, here you have 2yz. Here you have x squared simply, but here there is no z component, it's gone. So you have this recurrence. So at the given point, x value, y value, and so on, you plug those numbers, and you will get this gradient. So when you compute u in the direction of v, well, 0, 1, 1, and the magnitude of 0, 1, 1 vector is square root of 2. So you have this. The next what you have, the dot product, and you will get, you add them, always gradient will give you number. It is a scalar, the direction. There is a gradient field, but the gradient itself is a number. Then what is really happening? The rate of change of pressure over distance, that means this number 0.014 millibars, that means the pressure per kilometer. Thus, we express that as we move in the direction of V from Q, the pressure should increase because you have positive rate of change by about 0.14 millibars per kilometer. Is it clear, the process? Guys, I moved it, just you can do the calculation. That is my hope, yeah?
Yes.
Yeah, right. So I want to know actually the property of gradient. These are very important, and then we will really work with one example, and this will do it. Properties of gradient. If f of x, by the way, this gradient, I did it in general for 3D, but by decreasing one component, that means the z component, it can be applied for also two dimension. Properties of gradient, if f of x, y, z and q of x, y, z are differentiable and c is a constant, the gradient of the sum or difference of two functions equals the gradient sum or difference of those involved functions. This is linearity property. If you have some constant, a gradient of some constant multiple of the function is actually calculate the gradient and multiply it by the constant. All right. Then if you have product of two functions and find the gradient, what you have to do is apply the product rule of derivative what we learned before. So f multiplied by the gradient of g plus g multiplied by the gradient of f. In this case, order doesn't matter because addition is commutative. And the fourth, if f of t is differentiable function of one variable, then the gradient f of x, y, z can be applying chain rule, f prime of f of x, y, z times the gradient of f, the internal. So this is chain rule of gradient. The other one, I just forget, and you can see, I put it as fifth, the quotient rule also will be applied. The gradient of the ratio of two functions can be calculated by the gradient of the numerator function multiplied by the denominator function minus the numerator function multiplied by the gradient of the denominator function over the denominator function square. And I want you know that the gradient at the point is normal to the level surface of F at that point. Or if it is in 2D, for the level curve at that point F. Term, tangent planes to level surfaces if W is a function of three variable and differentiable at that point, x sub 0, y sub 0, z sub 0. Since the gradient is normal to the level surface, tangent plane to the level surface f of x, y, z equals k at the point will be given by this. The one example I showed you in 2 dimension, now it can be extended. That means the gradient of f dotted with the vector r minus r sub 0, and this will give you this formula is actually the tangent plane to the surface. Okay, well, why not you do this problem then? Find the unit normal vector n and the equation of the plane tangent to the level surface f of x, y, z, that is given by 4x squared plus 9y squared minus z squared minus 16 at the point 213. Please do that. So first we have to find the gradient. As you know, these are actually independently done. The partial derivative with respect to x is going to be 8x, and the partial derivative with respect to y is 18y, and minus 2z, and that is really quick. And now the gradient at the point 2, 1, and 3, that means 8 times 2, 18 times 1, and negative 2 times 3. And that will give us 16, 18, and negative 6. So, as you see, this is actually a normal vector. And let me make it actually capital N. And then, since we are asked to find the unit normal, what we are going to do is the unit normal N. Usually I use with a hat. That means the vector N divided by the norm of vector N. So then this is going to be 16, 18, negative 6 over square root of 16 squared plus 18 squared minus plus negative 6 squared. And it's already calculated. 16 over square root of 616. You can really add it and you can check it. I'm not going to spend time on this. So this is a unit. Now the unit normal, what we are asked is really founded. Then now the tangent plane at P. That means we have what? The gradient at x sub 0 into x minus x sub 0 plus the gradient at y sub 0 multiplied by y minus y sub 0 and plus the gradient at z sub 0 multiplied by z minus z sub 0 is going to be 0. That's it. This is really linear and equation of a plane. And you have 16, that is the gradient, and x minus 2 because the x component is 2. And this one is 18. And y minus 1. And plus, well, actually, let me make it minus 6 and z minus 3. So this is 16x minus 32 plus 18y y sub 0 is 1. So let us put the variable together, 16x plus 18y and minus 6z. And when we are adding this negative 32, negative 18 and by 18 will be cancelled. So 32 will go to the other side. We can really reduce it by 2. This is going to be 8x plus 9y minus 3z equals 16. And that's it. So what happened? If you look at this surface is actually a cylinder that is going to be really symmetric about the axis. If you want, by completing the square, you can really bring it. In other words, z squared equals 4x squared minus plus 9 y squared minus 16, and it is really cylinder of one head. And if we try to draw this roughly sketching, something like this, and then now what will happen? You are going to have a gradient vector which is really pointing this way. Let's say you are coming on the x direction 2, on the y direction 1, and on the z direction 3, let us say, and that's it. I put it a little bit high, and you get this one. This is really normal, and by normalizing, actually, you can get also unit normal, and the tangent plane that you are going to create is going to be tangent to this here, in that neighborhood. Because it is really expanded, and if it touches it, it doesn't mean anything. So that is really what we need to do. Okay, well, hopefully you have a clear idea about gradient. And when we talk about gradient vectors, vector fields, you will not be a stranger to it. Now, one of the things that we learn is chain rule of differentiation. So what is actually the accomplishment we need to have here? Upon completion of this section, you should be able to find the derivative of the composition of two or more variables using chain rule, and then find the derivative of implicitly defined function of two or more variables using implicit differentiation. Okay, what is chain rule? Chain rules rule is a formula for computing the derivative of composition of two or more functions. So you have two types of chain rule in general, two categories. Chain rule one, that means two variables of the original function composed with a function of single variable. So 2 to 1, that is what I mean by that. If z equals f of xy, that means the exterior function, and with x equals x of t and y is equal to y of t, a single parameter or variable t. Then the chain rule, using chain rule, dz dt, total differential, equals delta z delta x times dz dt plus delta z delta y dy dt. How do you do it? Where you have to draw the diagram, the tree diagram, actually. Look, you have the variable z, which has two inputs, x and y, and x in turn has one input, which is t, and y has another input, which is also t. And here, because it is involved with two variables, it is partial derivative dz dx. And this one, the rate of change, it is involved with single variable dx dt, total differential. And here, delta z, delta y, because it is involved with one, and this one dy dt. Then when you are going with one loop, you multiply. So the rate of change of z as a function of t will be then this route, delta z, delta x, multiplied by dx dt, plus delta z, delta y, multiplied by dz dy dt, dy dt, I'm sorry. And that is how the formula is derived. And actually, drawing tree diagram is really important. And I want you really remember that. And what I'm going to ask you is, well, you guys are familiar with, and I want do this. Let z equals the quantity xy plus 1 squared with x equals t squared and y is equal to 2t. Find dz dt. Go ahead. So what is really happening? Let us apply dz dx first. So this one, you can find the derivative of the external function 2 times x, y plus 1. And when you differentiate with respect to x times the derivative, this is going to be y. All right. Once we have done this, we can really do similar to dz dy. And it will be 2 times x, y plus 1. And the derivative of y is simply x. Okay, we have this. And then let us find the derivative dx dt, which is 2t, and dy dt equals 2. And by combining all this, you will have what? 2y xy plus 1 multiplied by 2t plus 2x xy plus 1 multiplied by 2. And that's it. And remember, this is dg dt. And it is a function of t. So x and y has to be replaced by that. So when you plug in to save time, this is what I gave you. So if you look at here, you have x plus xy plus 1 and xy plus 1. I can take out the common factor. And you have 2 times 2, and here 2 times 2 is 4. And then you have 40y. Ty is going to be here, and the remaining is x. I don't know why I put this 1 over here. Xy plus 1, that is what I'm supposed to do. All right, this is typo, and you understand, and this is it. Then when you plug actually in a place of x, which is t squared, in a place of y, 2t plus 1, and here also t and 2t, and here is this one t squared. And that is simplified to 12t squared times 2t cubed plus 1 quantity. And by the way, this would be even easier if we have done it like this. And let us check whether we have actually done it right or not. Z is actually x plus y, x times y plus 1 squared. And x is t squared, and y is 2t. And why not we make x z as a function of t simply? That means t squared multiplied by 2t plus 1 squared. And that will be 3t cubed. That quantity is squared. Now, if I want, because this is a function of single variable, total derivative as this thing, we are taking the derivative of this function. So, of course, you can apply chain rules here also. 2 times 3t cubed plus 1 times d of dt of what? 3t cubed plus 1. And that will give us actually the by the way, I don't know why I make it 3. This is 2. Nobody corrected me. This is 2. And so the derivative of the inner function is going to be 6t squared, simply. And then when we simplify, and by the way, this 6t squared is multiplying the quantity 2t squared plus 1 multiplied by 2. And 6 times 2 is 12. And you have here 2t cubed, which is really identical with what we have done. And these are, you are familiar. Please don't rush like myself and make error. For example, instead of writing 2t cubed, I wrote 3t cubed. Okay, well, let us see one application of chain rule, and that is this. Suppose the temperature at each point on a plane is given by t as a function of x and y is square root of x squared plus y squared degrees, and the bug's position at any time t second is given by x is equal to the quantity t minus 2 cubed and y equals the quantity t minus 2 squared. Determine the rate of change of temperature experienced by the bug as it passes through the point 1, 1. Go ahead. So first find the derivative with respect to x. And that will be, you remember the radical, the derivative of the square root is 1 over 2 times the square root of that quantity. And the derivative of the inner is twice of this, so 2 by 2 will be cancelled, simply x. Is it clear, guys?
Yes.
All right. Then the partial derivative of the temperature with respect to the position y is going to be the same by similar token. And we need to find dx dt. This is total differential, which is 3 into t minus 2 squared. And the last one is dy dt, 2 into t minus 1 minus 2. Then by the chain rule, as you know, the total rate of change of temperature with respect to time is going to be delta t dx the dt plus delta t delta y dy dt. And this will give us x square root of x squared plus y squared and the radical, and you have 3 into t minus 2 squared plus y over x squared plus y squared and 2 into t minus 2. You don't have to express actually everything in terms of t here because you are given a specific point. The problem is x and y are known. How about t? How do we find it? Well, we can't really determine that. When x is 1, since x is equal to t minus 2 cubed, and that equals 1, then what we have is t minus 2 is equal to 1 and t is equal to 3. And y equals t minus 2 squared, and that is also 1. From here, what do you get? Actually, the square of 1 is 1, so t minus 2 is equal to 1, and this is actually t also is 3. So you can see it is convenient. So, based on this, the rate of change of temperature with respect to time at the point 1, 1 is going to be 1 over square root of 2, because this is 1 and this is square root of 2, and you have 3 times 3 minus 1 squared plus 1 over square root of 2 and 2 times 3 minus 2, and that is what we have. And as you see, this is going to be 1 times 3 is 3.
I think that should be a 3 minus 1 squared, or 3 minus 2 squared.
Yeah, 3 minus 2 squared, I'm sorry. Otherwise, I cannot get 3. Thank you. And plus, this is 2 over the square root of 2. And this will give us actually 5 halves square root of 5. So the bug is experiencing 5 times 5 over 2 times square root of 5 degrees as it passes through the 0.11 for every actually 1 unit movement in that direction. And when you have function of 3 variables also, you can use chain rule 1. In other words, if for example w is equal to f of x, y, z, and x is a function of time, a variable t, and y is also a function of a single variable, then the tree diagram here, you have w, there are involved what? 3 variables, those are x, y, and z, and this is partial derivative, and x is in turn is a function of t, y also a function of t, and z is a function of t. And you have here total differential dx dt, dy dt, and dz dt. Therefore, in this case, it's going to be you multiply when you are going with one loop, and add when you are going to the other direction. You do the same thing here. And I'm not going to spend the time for this. If I give you function of 3 variables with a 1 input, you can handle it. And if you want, you can do this at home. Find dw dt if w is equal to x squared y plus y squared z, where x is equal to sine of t, y is equal to cosine of t, and z is equal to 5t. And your answer will be this one. You can really handle it. Now let us look at chain rule 2. In this case, actually, you are moving the input is going to be to the original function, and then the input variable is going to have also 2 variables, such as, for example, if z equals f of xy, with x is equal to a function of 2 variables u and v, likewise y. Then the partial derivative with respect to u for z is going to be, remember here we have partial derivative, and this is it. The reason why is, as I showed you, z is a function of 2 variables, x and y. X is a function of 2 variables in turn, u and v. Y likewise. Then what happens? When you have multiple variables, you do partial derivative, delta z, delta x, and delta z, delta y. And x is a function of 2 variables as well, delta x, delta u. And when you differentiate x with respect to v, delta x, delta v, likewise y. And as you are going to from one vein, you do multiplication and move to the second vein, you may do the other and you add it. So look, the destination for you go through this route, okay? The destination is du is going to be dz dx and dx du. That's it. But this one is involved with v. I'm not going to touch it, and then I'll go this way. And then follow this route. That is the first part. And the second part with respect to v is going to be dz dx. And here I have dy dz dy, delta z delta y. And now look, I started here, but my destination is delta v, so I will come through this. So delta x delta v. And likewise here, my destination is v, so I come through this and go to this way. So that is the formula right there. Okay, we have this. I want to really do the following. If z is equal to e raised to x sine of y, where x equals u times v squared and y equals u squared v, find delta z delta u and delta z delta v. Please do that. By the way, is it readable, guys? Okay, go ahead. Okay, we are running out of time, but we have to really do it. So the first thing that you have to do is the partial derivative with respect to x is going to be this, the exponential function sine of y is constant. So e to the x sine of y. Then when you differentiate with respect to y, e to the x is constant, but the derivative of sine is cosine. Likewise, when you differentiate with respect to u, v squared is constant, and that's what we get. And when you differentiate dx with respect to v, that means u is constant to uv. You do the same thing with respect to y, dy, du, and dy, dv. dy, du is to uv, and dy, dv is u squared. Then you plug it into the formula, you will get this. But since you are not asked like the previous one, given point, so what you have to do is, this has to be a function of u, everything. So, and it has to be a function of u and v, I'm sorry. So you have to really replace it and you'll get this. You do the same thing, you can accomplish this one. This is a really familiar concept. But we are going to use chain rule frequently in vector calculus. So that's why we are reviewing. Thank you. We'll continue from example 2 and we'll work with some Venn diagram and we'll generalize it. And we will work with implicit differentiation. And the last one is going to be for this chapter. I don't know whether we are going to finish it next week, tomorrow or not. Second order partial derivative. Yeah, that is also quick. Usually we use it to prove the heat equation, the Maxwell's equations, and so on. And we'll see those also because later on they will be handy. Thank you for your attention. I hope your time is worthwhile. Please keep up with the homework. And this week we will have our first test. Please be ready for that also. How was the quiz, by the way? Is it reasonable amount of time? Okay, good. Because I try to give you the highlights of the subject matter that you did, and I did give you reasonable amount of time, but there will be time crunch when you are in the classroom. So please work on your speed. We are spoiling you and you will forget. I don't want you guys relax when you go to the university. Not only knowing the knowledge, but also be efficient. The speed also doesn't matter. Work on that as well. Okay. Thank you. All right. Yes, sir. Yeah, yeah. I'm going to post them all actually. Chapter 14 all. Yes. Yeah. This afternoon, after I finish my class, I will do those. Yes. Thank you. All right. Take care.